Okay. Good morning, and thank you for joining me today. And as I get underway today, I just want to quickly note how great it is to be here in Atlanta for another KubeCon, surrounded by so much continued excitement and innovation around Kubernetes. And that's also why I'm so excited to be giving this specific talk today, because it highlights exactly how innovation in Kubernetes continues to influence some of the most mature and widely used software in some incredibly powerful ways. So with that quick intro out of the way, welcome to my talk on next-generation extension management using Kubernetes image volumes. And I'll start with a quick note about myself. My name is Andrew LeCure, and I manage the team behind pgo, the Postgres operator for Kubernetes. I've been involved in the pgo project for over 7 years now, and during this time, I've been fortunate to experience just how far Kubernetes has come from its humble beginnings managing stateful applications. And as Kubernetes only continues to mature and grow, it feels like we're at a real inflection point where Kubernetes not only supports the deployment of our favorite and most needed applications, but it's now directly enhancing the capabilities of those applications as well, as you will see today. And I'll start out by noting that when I mention next-generation extension management in the title of this talk, I'm specifically referring to the management of Postgres extensions. And for this talk today, I'm excited to highlight how two powerful new features, one in Kubernetes and one in the latest version of Postgres, come together to unlock a powerful new strategy for building, managing, and consuming Postgres extensions in a Kubernetes environment. By the end of this talk, my goal is that you will not only walk away with a streamlined and effective approach for getting your users the Postgres extensions they want and need, but I also want to end with a note about what this means for the Kubernetes platform and ecosystem as a whole. More specifically, I want to highlight how Kubernetes continues to influence the software we build in incredible new ways, sometimes 10 or even 20 plus years after its creation, as is the case for Postgres, as you will see today. So with that, let's now dig into exactly how Kubernetes image volumes enable a powerful new strategy for building, managing, and consuming Postgres extensions in your Kubernetes-based Postgres deployments. So what exactly are Postgres extensions? At a high level, Postgres extensions allow you to extend core Postgres functionality in powerful new ways. For instance, extensions can enable specialized data types and functions, additional security and logging, integrations with external systems, improved administration and management capabilities, support for additional languages within Postgres, and much, much more. See the table on the screen for some examples of popular extensions that meet a variety of different use cases. I do also want to note that while certain extensions come bundled with the core Postgres server, there is also a vast network of third-party and community-supported extensions available, with new extensions added all the time, not to mention some great frameworks for developing extensions for those interested in building their own custom extensions from scratch. Up on the screen is a quick example of how Postgres extensions are typically installed. And there are a few important things to note here. First and foremost, note that SQL commands are used to install, upgrade, and uninstall extensions. Additionally, some, but not all, extensions require additional configuration. More specifically, prior to installing certain extensions, the shared preload library setting must also be updated, as you can see on the screen. This is because certain extensions require specific libraries to be loaded into memory at server startup. And this is the setting that instructs Postgres to load those specific libraries. You can also configure this setting with multiple comma-separated values per the specific needs of the various extensions you're using, since it's quite common to be using more than one extension at a time. And while Postgres extensions are incredibly powerful, there are also challenges associated with building, installing, and managing Postgres extensions. First, because extensions need to be installed in a specific location on the Postgres server, they have limited deployment flexibility. For instance, when Postgres is containerized, this means a fresh build of a Postgres container is needed anytime a new extension is needed, or if you need to either update and/or remove an existing extension. This also means those packaging and distributing containerized Postgres need to put a lot of consideration into exactly how we build Postgres containers with various extensions baked in. While we know we can't include every single extension out there for a variety of reasons, whether that simply be to avoid bloat, for security reasons, licensing reasons, amongst various other reasons, this means we have to make the hard decisions around exactly what extensions to make available to our users. And that's really hard to do considering all the real-world use cases we see for many extensions out there. And it gets even messier considering users often want to use more than one extension, because now additional combinations and permutations of container builds are needed just to meet specific user needs and requirements. Additionally, this also means there are likely extensions in your running Postgres containers that you're not using. Obviously, from a security perspective, this isn't ideal, since unneeded and unused extensions not only add unnecessary bloat to your deployments, but they also increase the attack surface of your Postgres containers. And this is on top of other challenges, such as build and installation complexity. So there really isn't a one-size-fits-all answer for building, installing, and configuring Postgres extensions, which can make things quite tricky for users who are new to Postgres and are simply trying to find and install the various extensions they require. So what exactly has changed with extensions in the latest version of Postgres? Postgres 18, which was released in late September, adds a new configuration setting, specifically the extension control path setting that you see on the screen, that allows you to configure Postgres with a custom search path for locating extension files. And the big takeaway here is that there is no longer a single specific place on the Postgres server where extensions need to be installed. Instead, we can now tell Postgres to also look for extensions in additional user-defined locations. In other words, if I can mount a volume on a Postgres server containing extension files, then I can configure Postgres to look for extensions in that specific volume mount. And this is exactly where Kubernetes image volumes come into play. More specifically, image volumes provide a way to mount new volumes containing extension files into Postgres pods. Introduced as an alpha feature in Kubernetes version 1.31, image volumes are currently in a beta status as of Kubernetes version 1.34, where the feature also remains behind the image volumes feature gate. And this feature allows you to mount additional OCI container images directly into your Kubernetes pods. This gives the running containers in your pods read-only access to the contents of additional OCI images, adding additional flexibility to your deployment architectures. This includes enabling some powerful new use cases, such as streamlined CI pipelines, or the efficient distribution of large data sets, such as AI model weights or malware signatures. Additionally, there's the Postgres extension use case we're discussing in detail today, which involves sharing libraries and other associated extension files across multiple Postgres pods. So what exactly do image volumes look like? Up on the screen, I have an example of a pod spec with an image volume defined that is then mounted into a database container within that same pod spec. As you can see, image volumes are simply another volume type in the Kubernetes pod API. This means you can define image volumes under the volume section of your pod spec and then simply mount them into your containers using volume mounts. And before moving on, I simply want to highlight a few additional caveats with image volumes. First and foremost, in addition to turning on the image volumes feature gate in your Kubernetes cluster in order to use image volumes, the container runtime being used in your Kubernetes environment must also support image volumes. Fortunately, both Cryo and Containerd support image volumes in their latest releases, so these days you often only need to worry about flipping on the feature gate. And there are a few other caveats to note as well. For instance, image volumes need to be pulled down just like any other image, which means pulling large image volumes could add to pod startup time, while issues pulling image volumes could prevent the pod from starting at all. And of course, since we're giving users the ability to mount additional files into their running containers, this does mean vulnerable content could be introduced. So due diligence is still needed on the security and supply chain side of things to ensure we're not putting applications at risk when using image volumes. So now that we've introduced both Postgres extensions, including the changes made to Postgres extensions in Postgres 18, as well as Kubernetes image volumes, let's tie it all together. By building extensions as OCI container images, we can dynamically mount extensions into pods running Postgres. And by using the new extension control path setting in Postgres 18, we can then configure Postgres to look in those mounted image volumes for extension files. And that's exactly what you see on the screen here. We have a Postgres pod configured to mount the PostGIS extension, which adds geospatial capabilities to Postgres, as an image volume. And Postgres itself is then configured to look at the directory where that image is mounted to find extension files. This means any users using this Postgres server will be able to create and use the PostGIS extension in their various Postgres databases. And while giving users the ability to manually update their pod specs and configs to use image volumes is a powerful capability unto itself, we can streamline this even further by leveraging the Kubernetes operator pattern. And this is exactly what we've done in Pgo, the Postgres operator for Kubernetes. More specifically, Pgo can safely roll out changes to image volumes across the various database servers it's managing, allowing users to add or remove extensions packaged as OCI images at any time, all while also minimizing downtime to any end users and/or applications. And that's exactly what you see on the screen here, an example of adding an image volume extension using Pgo. On the left, we have a simple Postgres cluster spec defined that uses a Postgres image containing no community extensions. And on the bottom left, a create extension command is run to create an extension, specifically pgaudit, a popular extension that adds session and object logging to Postgres. And as you can see, the command fails due to missing extension files. Next, over on the right, the Postgres cluster spec has been updated with a custom image volume containing the pgaudit extension, while the extension control path setting has also been updated to instruct Postgres to look for extension files where that pgaudit image is mounted. And after a quick rollout, which is safely orchestrated by the Postgres operator to minimize downtime, the create extension command can be attempted again, which is what you see on the bottom right-hand side of the screen. And this time, the command will succeed. So now that we have an idea of what image volume extensions look like, let's talk about what it takes to build a containerized extension. And what you see on the screen here is an example of building the pg_node_mx extension for Postgres 18. This is an extension that is used to obtain C-group metrics from the Postgres server using SQL as part of the Pgo metrics and monitoring stack. As you can see in the Docker file on the screen, I start by installing the Postgres development packages and some other core Postgres dependencies, followed by some additional dependencies required by pg_node_mx. From there, I clone the pg_node_mx GitHub repository to obtain the extension source code before using make to build it. And finally, the resulting build is simply copied into a Scratch image, providing a very lightweight container that includes all pertinent pg_node_mx extension files only. So now that we've had a chance to take a look at what builds of image volume extensions look like, what exactly are the benefits? And over the next few slides, we'll discuss the various benefits listed on the screen. As you will see, these benefits directly address some of the challenges associated with Postgres extensions that we discussed earlier. And first up is streamlined development and integration. This includes both developing and integrating your own custom extensions, as well as building and integrating one of the many community-supported extensions that are available right now. And what is really cool with the strategy we're discussing today is that I don't even really need a local Postgres server to develop or test an extension, especially if I'm using a Postgres operator such as Pgo. After building an OCI image containing the extension files, I can simply push the image up to my image registry, where it can then be pulled into a running Postgres pod. This adds a ton of flexibility when integrating extensions into existing applications and services, because if I see an extension that I feel will provide value, I can quickly and easily integrate it into my own development databases, workflows, and processes. And this is really what the strategy we're discussing today is all about, ensuring users can fully leverage the incredible power of Postgres extensions, not only by more easily building and distributing their own custom extensions, but by also ensuring users are able to leverage the massive ecosystem of third-party and community-supported extensions to the fullest extent possible. And with new extensions added all the time, this means you can now get extensions into the hands of your developers and users in record time, Other engineers within your organization can benefit as well, since they simply need access to the image registry in order to start leveraging the same exact extensions within their own applications and development workflows. And on this slide is an example of an extension development workflow using image volumes. And in this diagram, we have a development team that is working on an AI agent and therefore needs a Postgres database with a pgvector extension installed. This is an extension that adds vector similarity search capabilities to Postgres. So in this example, let's imagine the development team wants to build and test the pgvector extension while then integrating it into the database for the agent they're building. And the process starts with a build of the pgvector extension on the top left-hand side of the screen. And I'll note that by using a base image containing common Postgres packages and dependencies, the development team can even avoid some of the challenges and complexities often associated with setting up an environment to build a Postgres extension. And once the extension has been built, it can then be pushed to an image registry, which is what you see in the center of the screen, where it can then be rolled out to the various Postgres clusters being used for development. And thanks to the Postgres operator handling the rollout, we can again avoid some of the challenges and complexities often associated with installing an extension in a running Postgres server. Instead, after providing the operator with a few simple lines of YAML, as we previously saw, the development team can quickly connect to the database to start testing it. The team can also easily integrate this change into the AI agent that's under development. For instance, a CI system, as you see on the bottom of the diagram, can detect and roll out the change to a database being used to test a deployment of the agent, all without requiring a local Postgres server install. In fact, everything you see on the screen here can be done without a local installation of Postgres by leveraging Kubernetes instead. And this benefit is amplified even further when targeting multiple versions of Postgres, since extensions need to be compiled against each major version of Postgres supported. And with Kubernetes being used more and more for development environments, it's exciting to see how this approach can streamline the extension development experience for those developing and maintaining Postgres extensions. So as you can see, the use of image volumes for Postgres extensions greatly reduces the friction associated with developing and integrating Postgres extensions. In other words, it's easier than ever before for development teams to try out and integrate Postgres extensions into the applications and services they're building. Whether building extensions from scratch or simply leveraging one of the many community-supported extensions that are available today. OK, so next up are the security benefits of image volume extensions. And as you will see, there are quite a few. First and foremost, with this approach, I can greatly reduce the attack surface of any running Postgres server, since I can mount the extension files I require only. And with an operator such as Pigo carefully rolling out pod changes, I can safely add additional extensions or remove any extensions that are currently installed at any time. And there are also supply chain benefits to this approach as well, especially since I can continue to use my existing OCI registries, infrastructure, and tooling. For example, on the Pigo project, we use Trivy extensively to scan our containers for vulnerabilities, which means we can now also use Trivy to scan our extension builds for vulnerabilities. And this is all while also using existing registry infrastructure to easily distribute the latest extension updates and patches across the various Postgres clusters that I'm responsible for managing. And that's exactly what is shown on this screen, an example of how easy it is to rebuild and deploy a patch for an extension across a fleet of Postgres clusters using image volumes. So on this slide, let's imagine we're on the operations team that is responsible for ensuring the latest Postgres extension updates are built, deployed, and installed. And in this example, let's imagine we're creating a fresh build to pull in the latest updates for the pgvector extension. Once the extension is built by the ops team, they can simply push it up to the image registry in the center of the screen, where the various Postgres clusters using that extension can then pull it down. And of course, we once again have the operator safely rolling out or orchestrating the rollout of the patch when this occurs to minimize downtime. This is also a great chance to note that the patch isn't rolled out to every single Postgres cluster. In the past, this wouldn't have been possible, since a full server rebuild would have been rolled out to every Postgres cluster anytime an extension is updated, whether the extension was being used or not. But with image volumes, we can configure each cluster with only the extension files and libraries it requires. This means clusters that are not using the pgvector extension, for instance, cluster C in the example on the screen, can simply ignore the update. Additionally, this is a great chance to highlight some of the supply chain benefits of image volume extensions, such as simple SBOM generation and security scanning. For instance, on the screen, you can see an example of SBOM generation for the pgvector extension using SIFT, along with a security scan using Gripe. As you can see, since we're dealing with a single library file only for a typical Postgres extension, these scans are typically quick and painless, especially considering we're also using a scratch image and therefore don't need to worry about erroneous vulnerabilities from operating system packages. This means it's very easy to assess and, more importantly, be confident in the security posture of an extension as it's rolled out. And on this next slide, you can simply see how these supply chain benefits can be amplified even further using a registry solution such as Harbor, which puts SBOM, scan results, image signing information, architecture information, and more right at the user's fingertips. Not to mention simply providing a clean user interface for searching for and discovering new extensions. So by using OCI images for extensions with a registry solution such as Harbor, we're also empowering users to discover and make good decisions about what extensions to include in their own Postgres cluster deployments. Continuing with this theme for one more slide, I also want to highlight how this strategy greatly facilitates the maintenance of Postgres containers. And this not only includes the maintenance of Postgres extensions, but also the Postgres server itself. And for those of us packaging and maintaining containerized Postgres, the strategy we're discussing today means we no longer need to make hard decisions around exactly how to package extensions within the Postgres server. Rather, we can simply focus on building individual extensions separately from Postgres itself, while then empowering users to pick and choose the exact extensions they want to use per their specific needs and requirements. At the same time, we can also roll out new versions of the Postgres server. For instance, the quarterly patches are released by the Postgres community without having to rebuild each and every extension at the same time. And of course, since image volumes make it easy to integrate new extensions built as OCI images, we can also set up CI pipelines to easily test new builds of extensions against any new builds of Postgres. And while so far today we've focused on the extension system baked into Postgres, I'd like to loosen the definition of extension a bit for the next slide. This is because there are even additional ways Kubernetes image volumes can also be used to extend core Postgres functionality. On this slide, I highlight yet another way image volumes can be combined with a brand new feature in Postgres 18, more specifically, OAuth 2.0 authentication. And as part of the new OAuth implementation within Postgres, users must configure Postgres to use a specific validator library to validate tokens during the OAuth authentication process. This enables support for OAuth tokens of all shapes and sizes by making the user responsible for configuring Postgres to validate tokens according to the specific and often unique tokens generated by their own identity and access management systems. To provide a quick example, if your organization is using Google authentication, which uses OpenID Connect, a superset of OAuth 2.0, you could build a validator library that is able to validate OAuth tokens from Google. More importantly, however, this also means validator libraries can be built and distributed as OCI images. Similar to image volume extensions, we can simply mount these images into running Postgres containers using image volumes, while then configuring Postgres, specifically using the OAuth validator library setting you see on the screen, to look in those image volumes for validator library files. This means we don't have to worry about the specific implementation details of the OAuth tokens we're using when building and distributing the Postgres server. Instead, we can simply plug in the libraries needed to validate any flavor of OAuth token at any time. OK, so now that we've had a chance to take a deep dive into using image volumes in multiple cool ways with Postgres, I'd like to start wrapping things up, starting with a summary. And what we've seen today is that two powerful new features, one in Postgres and one in Kubernetes, come together to unlock a powerful new strategy for building, distributing, and consuming Postgres extensions. More specifically, by packaging Postgres extensions as OCI images, we can then mount them into containers running Postgres using the new image volume feature within Kubernetes. And then, using the new extension control path setting, we can configure Postgres to look in those mounted OCI images for extension files. This approach to managing extensions has a variety of benefits, including streamlined builds, development and integration, improved security and supply chain management, and better extension discovery. Most importantly, however, this strategy ensures Postgres users have the flexibility to install the specific extensions they need per their specific database workloads, requirements, and use cases. And we're also now seeing additional use cases for image volumes in Postgres, such as dynamically mounting validator libraries for OAuth 2.0 authentication. And while the strategy we've discussed today is incredibly powerful from a technical perspective, as I conclude today, I want to end with a quick note about what I feel this also means about the current state of the Kubernetes platform and ecosystem. And this talk today highlights just how far we've come when it comes to managing stateful applications in Kubernetes. Whereas 5 or so years ago, many were struggling to get their first databases up and running in Kubernetes, we now have Kubernetes influencing the design of Postgres itself, with Kubernetes-based deployments of Postgres directly influencing the introduction of the extension control path setting that we discussed today. This means for software such as Postgres, there are now even more distinct advantages to running Postgres databases inside of containers and Kubernetes. And considering the power of the Postgres extension ecosystem, getting the right Postgres extensions into the hands of those who want and need them truly is an advantage that cannot be ignored. And I'm excited to see even more innovations like this moving forward. So with that, I simply want to say thank you for joining me today. I really appreciate you taking the time to listen to my talk on next-generation extension management in Kubernetes. And if you'd like to continue the conversation around anything I discussed today, come find me around the Snowflake booth. I'd love to chat with you about your favorite extensions and some of the challenges you faced using Postgres extensions. Thanks again, and I hope you have a fantastic rest of your day. And I think I have a couple minutes for questions if anyone has any questions. Yeah, go ahead.
So that depends on features of Postgres 18, yeah?
Correct, yeah.
Is there a way to sort of hack that together with maybe volumes with older versions?
I haven't really looked at it in terms of an older version of Postgres. You know, really our focus has just been kind of on the latest version. I know it's a little frustrating because most people aren't on the latest and greatest version of Postgres. 18 was just released. I know most people typically wait a couple patch versions at a minimum before upgrading. So yeah, right now our focus is really just on 18 and beyond, you know, where this feature is officially supported. So looking at backporting it or anything like that, that just hasn't been in scope for us so far. Yeah. Yeah. Well, and the new extension control path setting that is required to do this, that is only available in Postgres 18. So that setting is not in older versions of Postgres. Yeah. So it would probably be quite a challenge to try to get that into older versions of Postgres. Yeah. Someone else? Oh, over there.
This makes testing your images somewhat more complicated, yes?
I'm sorry?
This makes testing your images somewhat more complicated, yes?
Well, I think there's some benefits, you know, because I think you can set up some pretty cool CI pipelines with this sort of approach, you know, and that's one of the benefits of image volume extensions just in general outside of Postgres. A lot of people are leveraging this to make, you know, CI pipelines and testing a little easier because, you know, you can separate your different binaries and kind of bring them together when you're creating your pods and stuff to test everything out. And we've seen some of those similar benefits with extensions where, you know, we can just have the core Postgres server install, we can set up pipelines that make it easy to pull in some of these other extensions we're experimenting with as OCI images, and it makes it really easy to just kind of take that extension we built, kind of slap it on the pod, try to create the extension and test it out real quick. Even though everything isn't right on the Postgres, right there on the Postgres server, we're actually seeing a lot of benefits because now the developers and the ops team, they can just kind of go nuts experimenting with just building the extension. They don't have to build the whole Postgres server or anything like that. So we're seeing a lot more activity with engineers building different extensions or trying others out, and image volumes make it easy to just kind of bring that new extension into the pod, test it out, and see if it actually works. So we're finding that it actually reduces friction with testing at the end of the day with new extensions. Yeah, go ahead.
You mentioned adding supply chain artifacts to the images, such as SBOMs, signatures. Are there particular tools that the community is using for the community extensions? Or is that something that's just like, because we're doing OCI, this is a possibility?
Yeah, it's something. It's the latter because it's OCI. It's a possibility. So even though this new feature had Kubernetes in mind and things like that, Postgres really wasn't thinking about it from that specific perspective. So yeah, now that it's OCI, that kind of opens that door for us to leverage some of that exact tooling for extensions. And the beauty of it is these extension builds are so quick and painless typically. There are some extensions that, like PLV8's a great example because it brings in a full JavaScript engine. It's a big build and it's a pretty heavy, but a lot of extensions are super simple and small. So it's nice, a lot of us are already sitting on top of all this great OCI infrastructure for supply chain management. And now we can just continue to leverage that. But like you said, that's just the fact that we can now use OCI and stuff, to build the extensions, that we get to leverage some of that stuff as well, which is a nice win. Yeah. Yes. Sorry, having a little trouble hearing.
Talk a little louder. So I have a question about the underlying image volume functionality. Do you have to worry about the base image and the extension image colliding with each other in terms of paths?
I haven't seen any issues with that. Like right here, we're just using Scratch images. So, there's not even an operating system in these images we're building. But in general, I haven't seen any issues mounting any image to, an existing pod. Because really what Kubernetes, it's just read-only access. You're not running things in there. You're just kind of using it as a means to get access to files. It's another way to distribute files, data, things like that. So, the underlying OS of these image volumes that you're mounting doesn't seem to really matter at the end of the day. You're just getting to the access to the files within that container. Yeah. Cool. Awesome. Okay. Well, thank you so much. Hope everyone has a great day. Thank you.